I want to make sure that you realize your entire education was leading up to this and was useful for this. I have actually used this. When is the solution periodic? I've actually used this. Did a problem on West Nile. I did a model on West Nile back when it first hit this area. And I needed to show that my solutions did not have a periodic solution. So we care. Sometimes we want it to have a periodic solution. Sometimes we don't want it to have a periodic solution. And so that's what this part is important about. So what's a definition? We start out with a differential equation. Let's just do non-autonomous, autonomous. If it's non-autonomous, it gets harder. If x of t plus t is equal to x of t, and t is a minimum of all s such that x of t plus s equals x t. That's not how your book has it, but they say it. I think that in the last part of your book, they have Fourier transforms. Fourier transforms are used all the time. They're used in your Fitbits, Garmin's, whatever you use to Apple Watches to capture movement. When you're walking, it's periodic movement. So the Fourier transforms are actually what picks that up. So we really care about periodic movement. In that case, you want to detect when someone is moving or running, which is very little in the United States. There's actually a friend of mine that developed an accelerometer that sits on a pair of glasses. The hardest thing in nutrition is to measure the most important measurement, which is what is someone eating and when are they eating, about their eating. They're using self-report, which is highly suspect. And so he developed these glasses that has an accelerometer in it. And if you notice, your temple moves when you chew. But he has to automatically detect. You don't want those glasses recording everything because then you have privacy issues. You want it to record only when it detects that person's eating. So that's another place we want that cyclic movement to be noticed and picked up. And so that's a good example of why we care about something being periodic. For linear equations, let's see how much we remember. When does this thing helping you out with your note cards here, when does this thing have a periodic solution? There's only really one case. Yeah, it's a condition on A. Remember what the Venezuelan guy said? His name is Hugo. If you know the eigenvalues, you know everything. So what set of eigenvalues will tell you when you have a periodic solution? Not real. But I could have like A plus BI. What happens when the A is positive? Right, so that's not a periodic solution because it's going to, right? What if it's A is negative, right? So then it's stable, then it's converted to an equilibrium point. That's not periodic. What's the only case that you have when you're going to get a periodic solution? Zero real part. And I think that was Dr. Groves that talked about that. That's the only time. And I think she called it a center. Does that sound familiar? In that case, it's a center, and it doesn't have, they don't have a stability. It's just called a center. But the way that you want to think about this theoretically from a mathematician's point of view is sometimes at the end of the day, it converges to an equilibrium. Sometimes at the end of the day, it might converge to that periodic solution. So we call that an omega limit set. At the end of the what does it converge to? In this case, it will converge to an entirely periodic solution. So that being a center is not just good enough. You probably want to know more than that. For linear things, though, pretty boring. You'd expect that to be learned already. I went down this rabbit hole, and I think it's good for you to see these nasty computations. I don't know how much Dr. Grove has done. Probably a lot. So let's go through this example in nauseam. It's nonlinear. All right. You've listened to me enough. Find the equilibrium points. Do what you need to do. Take boards to do it so you wake up a little bit.